A basis for a vector space V is the smallest, most efficient set of vectors that can still reach every single point in that space. To qualify, it has to satisfy two properties at once, spanning the whole space and being linearly independent. Let's confirm this for the standard basis of the real numbers cubed. E sub 1 equals the vector 1, 0, 0, E sub 2 equals the vector 0, 1, 0, and E sub 3 equals the vector 0, 0, 1. First, spanning any vector, the vector ABC can be written as A times E sub 1 plus B times E sub 2 plus C times E sub 3. So these three vectors reach every single point in the space. Second, independence. If C sub 1 times E sub 1 plus C sub 2 times E sub 2 plus C sub 3 times E sub 3 equals the zero vector, then the only solution is C sub 1 equals C sub 2 equals C sub 3 equals 0, so none of them is redundant. Because both properties hold, this set is a basis, and the number of vectors in it, 3, is called the dimension of the space. Now let's work a harder example. Finding a basis for a plane W living inside the real numbers cubed, defined by one equation, x minus y plus 2z equals 0. Solve for the dependent variable, x. Rearranging gives x equals y minus 2z. Substitute this back into the general vector. The vector x, y, z becomes y times the vector 1, 1, 0 plus z times the vector negative 2, 0, 1, since x, y, and z are now written purely in terms of the free variables y and z. This shows that W equals the span of the vector 1, 1, 0 and the vector negative 2, 0, 1, so these two vectors span the plane. Check independence. Neither vector is a scalar multiple of the other, since their entries don't line up under any single scaling factor, so the set is linearly independent. Both properties hold, so these two vectors form a basis for W, and the number of vectors in that basis, 2, is the dimension of W, literally how many independent directions the plane has. Like and follow for more math tutorials, one idea at a time, nothing rushed.